Hey folks, onwards and upwards into the natural logarithmic function and differentiation. So by definition, a natural logarithmic function is defined to be the area under the curve 1 over x from 0 to infinity, not including 0. And we do not include 0 because my cat just totally distracted me. I'm sorry. The natural logarithm. Okay. Back up real quick. The area under the curve from 0 to 1 is actually negative. I don't want to get into that too much. I'm trying not to over-explain because there's some pretty complicated things in here that you're not gonna be introduced to until we're out of AB material and in BC material. So it's basically the area under the curve from 1 to infinity. I really don't want to go into that some more. If I have to, if you're super confused, I will explain it to you in a tutoring session. So a logarithmic function is the area under the curve of 1 over x, basically. So Leonard Euler discovered that there is this number that occurs when you take the limit as n approaches infinity of 1 plus 1 over n to the nth, which can be rewritten as shown. And that is 2.7183 yada yada. Right? Okay, so E is this limit, and the inverse, I'm sorry, I'm not thinking clearly. Oh, I'm sorry, I can't once I say something, I can't tape over it. I know that's not a real thing, but you know what I mean. I can't record over it. Okay, so by definition, y equals the natural log of x and y equals e to the x are inverses. Okay, we got through that. Sorry, I totally over-explained. All you need to know, really, is that these two are inverses, and we are talking about the natural log of x. The rest is like a huge bit of this course, but it's later in the course. You need to know what the natural log is, and you need to know that it's the inverse of e to the x. The domain of y equals the natural log of x is 0 to infinity, not including 0, and the range of the natural log of x is negative infinity to infinity, because your graph looks something like, I don't know, boop, 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 there. So your domain starts at 0. Oh, this is the y-axis. This is the x-axis. So your domain starts at 0 and keeps going on to positive infinity, and your range goes from negative infinity to infinity. The graph of y equals the natural log of x is continuous, increasing, and 1 to 1. 1 to 1 is something we have not talked about much before getting to calculus. It means for every x there is one y, for every y there is one x. And the graph is concave down. Okay, for every x there is one y, for every y there is one x. That is what 1 to 1 means. Now concave down is not something that we have talked about, and I'm going to talk about it very quickly. Anything that is concave down, if you you were to drop a penny on that surface, right here, it would roll down and off of that surface. Same with this, concave down. That's what concave down means. Now, you need to remember that the derivative of the natural log of some function is 1 over whatever you're taking the natural log of times the derivative of what you're taking the natural log of. So we go through some old properties from, I believe, Algebra 2. The natural log of 1 is 0, the natural log of e is 1, the natural log of a times b is the natural log of a plus the natural log of b. The natural log of a divided by b is the natural log of a minus the natural log of b, and the natural log of a to the n equals, bringing the power up front, n natural log of a. Okay, we have a typo. Then we go on to our first example. We're going to write this as a sum, difference, or multiple of logs. So the first thing we're going to do is we're going to separate it into a subtraction problem. Once we've done that, we're going to put our powers out front. And there we go. Sometimes it's going to be in our best interest to separate out our logarithms like that. And sometimes it's going to be in our best interest in a problem to squish it together as a single logarithm. So we're going to look at this next one, and we're going to move our powers up, and then we're going to change that from an addition to a multiplication. And we're not really switching it, but I'm using the wrong descriptor. We're using our properties of logarithms to rewrite it. And so there's no, switching is just the wrong word. Then we come down to our next example where we're looking at the natural log of 2x. And we need to find the derivative. In order to find the derivative, we, according to the directions, which are on the previous page, that's what I thought, we put 1 over 2x times the derivative of what we were taking the natural log of. And that simplifies to 1 over x. Okay. And then, it looks like we are missing our definition. So I'm going to put that back on that previous page. And there is our definition, which should be just below this on your PDF. I somehow missed it when I was taking pictures for these notes. So your derivative of the natural log of u will always be 1 over u times the derivative of whatever you're taking the natural log of. Next up, the derivative of the natural log of x squared plus 1 will be 1 over x squared plus 1, all times the derivative of that which you are taking the natural log of, and the derivative of x squared plus 1 would be 2x. I'm having a terrible time with my pen this evening. We simplify, we get 2x over x squared plus 1. On this next one, we need to use product rule, so we take the derivative of the first times the regular of the second plus the regular of the second times the regular of the first times the derivative of the second. And that gives us the natural log of x plus 1. On the next one, we kind of have chain rule inception going on here. So I'm going to rewrite it to make it easier to see our exponent. Okay, so I rewrote it so that that 1/2, or that square root, was written as the power of 1/2. Oh my goodness, and I took the derivative without meaning to. I'm really tired. Okay, and that isn't even the real derivative. So that's what we have going on. We can, or you can, if you would like, rewrite it with that power out front. That's what I meant to write. Now, we are going to take the power. I don't know why I'm sorry, guys. We're going to take the derivative, and the derivative would be 1 over x plus 1 times the derivative of what we're taking the natural log of, which would just be 1. And most of you are going to want to keep it that way. Some of you like to simplify everything, and that's okay. Just be careful. And we get, for our derivative, 1 over 2x plus 2. Now we have another kind of derivative inception. The derivative of natural log would be 1 over the natural log. Now we need to take the derivative of what we're taking the natural log of, and we are taking the natural log of the natural log. And the derivative of the inner natural log would be 1 over x. So our actual y prime here can be written any of these three ways. Now we're going to look at the natural log of x. Well, the derivative of the outer function would be 1 over the natural log of x, and the derivative of the inner function being, oh my gosh, my pen won't write, the natural log of x would be 1 over x. So the whole thing would be 1 over x natural log of x. Next one, the natural log of x cubed is the same as 3 natural log of x. So when we take the derivative, we get 3 times 1 over x, which simplifies to 3 over x. Okay, so even if we did it the long way around, where we did not bring that power down first, if we did it the long way around like this, we would still get 3 over x as our derivative. Okay, show that y equals x natural log of x minus 4x is a solution to the differential equation x plus y minus xy prime equals 0. The first question you should ask yourself is, what the heck? Well, what do we know? We don't know much, but we do know that we have a y here, and we know that we're looking for a y prime in there. So let's figure out what y prime is. Okay, so the derivative of the first would be the derivative of x, which is 1, natural log of x, that's the normal of the second, plus the normal of the first, which would be x, times the derivative of the second. The derivative of natural log of x is 1 over x, minus 4x, the derivative of that is just minus 4. Once we've done that little tiny piece, we are going to replace y with its value and y prime with its value. So again, we're trying to verify that this particular equation works, we're going to replace y with its value and y prime with its value. And we're going to ask ourselves if that, in fact, actually equals 0. And then we combine our like terms. We see that we have x natural log of x here, negative x natural log of x there. We see that we have positive 4x between those two, and negative 4x right there, and that does in fact equal 0. And every once in a while I have a student who writes this. Fabulous, you proved it. That's all you needed to do. That, by the way, that means nothing to me. You don't need to write that. Some people like to write that. Yay, it means you're done with the proof. Okay, moving right along. Okay, we're going to talk about exponential functions differentiation. And in order to talk about that, you need to know, I don't know why it says you learned in pre-cal. I hope you learned that in Algebra 2. Y equals log base b of x means that x equals b to the y, and y equals the natural log of x means that x equals e to the y. I really hope you learned those in Algebra 2. But in any case, I'm going to go through some processes here that involve not log rolling. For some people, like me, log rolling is mystifying. So instead of log rolling, I'm going to go through the actual process to show you how to get rid of either the e or the logarithm. So rather than log rolling, I'm going to take the natural log of both sides because I know the natural log is the inverse of a function that is e to the. So when you do that, you end up with x plus 1, because the natural log and the e cancel, equals the natural log of 7. If you're a fan of log rolling, you skip this very first step. It's okay with me if you're a fan of log rolling. I just happen to not be a fan of it. It feels like magic math to me. So that's just my personal preference, and I'm bringing it up for those to whom log rolling seems like magic math. Okay, in this next step, you want to stop. Don't bother changing that into a decimal unless you're asked to, which you are. Which brings me to the big issue on the test. And I just about cried a river because some people, there are maybe about 5 of you, who forgot approximate signs and 3 decimal places. Dun, dun, dun. Okay, on this next one, we have a natural log. We need to do this the opposite. So we need to e to the both sides. I don't know how else to describe what I'm doing. So e to the, it's a new thing. So we e to the both sides to get rid of it, and to get rid of the natural log. And we end up with e to the 5th equals 2x minus 3, which is what you would have gotten if you would have log rolled. Under ordinary circumstances, I would recommend stopping right there, but the directions do say that you need to go to 3 decimal places. Anytime you are asked to approximate a decimal in calculus, unless it specifies otherwise, you want to go to 3 decimal places. The derivative of an e to the function, e to the u, the derivative of e to the u will always be e to the u times the derivative of that u, And you did see that before the last test. I made sure you did in one of the circuits. So we're going to look at e to the 3x squared. E to the is a super weird thing. I mean, I know I'm not calling it what it really is. Just let's be clear about that. It's just easier to talk about. So it stays the same, but you also have to take the derivative of the power. And the derivative of the power in this case is 6x. Write it a little prettier and you get 6x e to the 3x squared. On B, we need to take the derivative of the outer function, and the outer function is actually the squared, so the outermost layer of that onion is actually the function squared. So I'm going to rewrite that so you can see that. So all I've done right here is taken the derivative of that outer layer. Now we're going to take the derivative of sine, and the derivative of sine is cosine. And then we need to look at our innermost layer, which is e to the x. And the derivative of e to the x is e to the x. Finally, we need to write it pretty. Once you've written it pretty, you can move on to the next one. And C says the natural log of, we're going to take the derivative of the natural log of 4 plus e to the 3x. So when we do that, the derivative of any natural log is 1 over whatever you're taking the natural log of. Then we need to take the derivative of what you're taking the natural log of, which is 4 plus e to the 3x, and the derivative of that would be e to the 3x. Now you need to take the derivative of the power, which would be 3, and now we need to rewrite it in a pretty way. And we've got it. Now on to D. We're taking the natural log of something, so that is our outer function, but wait, there's more. Think about it. We've got the natural log of e. We could actually bring our power out. So let's bring x cubed out front. And think about the natural log of e. Well, the natural log of e is just 1. So really, all we really have is y equals x cubed. What's the oh, y'all, my pen is really malfunctioning tonight. Y equals x cubed. And our derivative would be 3x squared. Oh. Now, moving right along, we have the natural log of a quotient, which can be written instead as the difference of natural logs. So we're looking at the derivative of the natural log of 3 plus e to the x, which would give us 1 over 3 plus e to the x, all times the derivative of the thing that we're taking the natural log of, minus 1 over 3 minus e to the x, and then we need to take the derivative of minus 3 to the x, which would give us negative e to the x. Now we need to write it pretty, and then we'll be done. Okay. We have written it pretty, and we're on to F. F involves product rule. So we need to take the derivative of the first times the normal of the second plus the normal of the first times the derivative of the second. I don't know if I said that right. Anyway, derivative of the first times the normal of the second plus the normal of the first times the derivative of the second. That'll work. I kept track of what I was saying that time. Okay, so the derivative of the first times the normal of the second plus the normal of the first times the derivative of the second. And we simplify that a bit and make it look pretty. And there we go. Now we're going to use implicit differentiation to find dy dx in exy plus x squared minus y squared. We have some e to the x craziness. We have product rule on top. So we've got some crazy things going on. And if you look carefully, I brought down the normal, the e to the power. Then I took the derivative of the power, which would be the derivative of the first, times the normal of the second, plus the normal of the first, times the derivative of the second. The derivative of x squared would just be 2x, and the derivative of y squared would be 2y dy dx. Oops, and that whole thing equals 0, because the derivative of 10 is 0. Now we factor out we get the dy terms on one side and everything else on the other. We're going to factor out a dy dx so that we can solve for dy dx. And there we go. On the next one, it asks for the relative extrema, the points of inflection, and sketch the graph. You don't know how to do any of that. And I want to acknowledge that. That this has been thrown in, and I don't feel comfortable doing a single bit of it. I think you might become more than mildly overwhelmed. So we will not be doing this problem. And if you see anything on your assignment that says anything about relative extrema, points of inflection, I want you to skip that problem. I don't know what it's doing here. It doesn't belong here. Booty, 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 rocking everywhere. I don't know if you've seen that ad. My little 10-year-old niece never stops talking about that stupid ad. There we go, a little cartoon. This is me at a concert. As you can see, I'm in African garb. This is me down in the lower corner, shaking hands with my favorite singer. Her name is Angelique Kidjo. She has won she's won more Grammys or more awards than Sting. I can't remember which. And these are all the places I have lived in my lifetime. You will be hearing more about actually New Glarus, Wisconsin next time. I hope you all have fun. Can't wait to see your faces live and in person. Y'all take care. Bye.